So let's begin with number 2 on the exam 3. I believe that the solution is also available on Canvas page. I don't know where it is. You kind of have to find it. So this problem has 2 parts. All right, grab the So for number 2, the first part, it says using ansatz y equals x to the lambda to find the linearly independent solutions, basically the base solutions of this homogeneous equation x squared y double prime minus 6y equals 0. So if we were given an ansatz and use it to solve, what we do is we just going to take it, plug into the differential equation. So we have to find the first derivative because we need the second derivative. To find the first derivative here, what we're going to do is that we're just going to use the power rule, right? Because lambda is a constant. This is the x to the power, so we use the power rule. So we got lambda x to the lambda minus 1. And then we're going to find the second derivative using power rule again. The first lambda just stays. And then we're going to move the exponent to the front. So that's a lambda minus 1, x to the lambda minus 2. And then we can take the second derivative and the y put into this differential equation. So that's going to give us x squared times lambda minus 1, x to the lambda minus 2, minus 6y, which is 6 times x to the lambda, equals 0. If we simplify the 2x terms in the first 2x terms in the first term, we just get x to the lambda, so that's good. So we have lambda minus 1, x to the lambda minus 6, x to the lambda equals 0. Then we can factor it out. Factor out x to the lambda. We end up with, I'm also going to distribute the lambda into the parentheses. We got lambda squared minus lambda minus 6 equals 0. And if you look at the instruction, I believe it says x cannot be 0. So if x cannot be 0, then x to the lambda cannot be 0. Therefore, this parenthesis has to be 0. So note, given x cannot equal to 0, so this part cannot equal to 0. Therefore, lambda squared minus lambda minus 6 must be 0. I just want to point out that the process is similar to what we did using e to the lambda x, but the terms are different, especially the second derivative. When we use the power rule twice, we get lambda times lambda minus 1 as a coefficient. So if we solve for lambda here, we got lambda minus 3, lambda plus 2 equals 0. We get lambda equals 3, lambda equals negative 2. And therefore we have 2 solutions that are linearly independent. y1 equals x cubed, y2 equals x to the negative 2. Any questions about what I did in this first part? I know that we haven't practiced this. I don't think we did it in recitation at all. Maybe we did it a long time ago. It also wasn't in the homework. Maybe that's probably why that, when you would study it, you didn't really study this type of question. That's understandable. But the process is similar to what we have done, right? So now we can write down the homogeneous solution if we want for this problem. So that's going to be c1 x cubed plus c2 x to the negative 2. Anyway, I just want to point out that Professor Gibson probably went back to all the exams and take a look at number 2, and I don't know which one he picked or what kind of mistake he gave you more points. So there was a few exams that he actually corrected the grading by giving a couple more points. So if you, I'm not sure what type of mistakes that he picked to give back some points. He didn't tell us.
I did the same thing with Stephen, the other recitation.
Yeah.
I started it right where I solved with x to the lambda.
Yep.
Well, then I did like the w and
Yep.
solved it. I did
e to the lambda x.
But I did the first part with x to the lambda and then switched it.
Okay. I would say, like this is just.
That is the only mistake. The other question I did right and everything else.
Right.
By doing the e to the lambda x
right.
and causing me to have to double it.
Right. Do you feel like the grading was a bit harsh?
Yeah, because I got 25 points off for that one mistake.
Okay. I'm not saying whether that's right or wrong because I didn't grade that problem, but I would say it's definitely worth to ask, if it's possible based on the most of the correct work I do, can I get more points or something like that?
Okay.
Yeah, it's apply to everyone. That's all. So the next part is actually to solve this non-homogeneous equation, x squared y double prime minus 6y equals 2x to the 4th. We already did we did sort of half of the work, right? Because we find the homogeneous solution to the homogeneous equation. It's the same homogeneous solution here, so we don't have to do more work. So that's still valid. This is still valid. We're just going to use them. And then we need to find the particular solution. But before we do that, this is something I sometimes forget, but you should try to remember is that when you use variation of parameters, this coefficient must be 1 when using variation of parameters. So before we do anything, we need to make sure that's a 1. So that means we have to divide by x squared from all terms. So we get y double prime minus 6 over x squared y equals 2x to the 4th divided by x squared, so 2x squared. So this is the equation that we're going to work with. And not the one that's given, because the one we were given doesn't have a 1 in front of y double prime. This is the one that we're going to work with. The only thing that matters is actually the f of x. So now we're going to apply the trick that Professor Gibson shared, or use a different way, solving system of equations. But if you use the Wronskian, so W is going to be the determinant of this matrix, y1, y2, y1 prime, y2 prime. And the y1, y2 are from the homogeneous solution when we solve for it. So that's going to be x cubed, x to the negative 2. Then we're going to take the derivatives. So 3x squared, negative 2x to the negative 3. And to find the determinant, so that's going to be, so if you remember, we're going to multiply this diagonal first, subtract the other diagonal. So that's going to be x cubed times negative 2x to the negative 3 minus x to the negative 2 times 3x squared. That's going to be negative 2 from here minus 3 from here, and negative 5. And all the x terms, when you multiply them, you get x to 0, so it all becomes 1. And then from the u1 prime is going to be 1 over Wronskian times the determinant of this matrix. This matrix is similar to the Wronskian. For u1 prime, it's going to be the first column replaced with 0 f of x. The second one stays the same. So that's going to be 0 f of x. y2 would be same. y2 prime is the same. So that's going to be 1 over negative 5. The determinant of 0, f of x is 2x squared. This is the f of x here. And then x to the negative 2, negative 2x to the negative 3. And that's going to be negative 1 over 5 times 0 minus x to the negative 2, 2x squared. So that's going to be negative, positive 2 over 5. And then we have to integrate to find u1. So that's going to be 2 over 5x. And then we can use the same approach to find u2 prime, which is 1 over the Wronskian times the determinant of this matrix. And then this matrix is going to be just like the Wronskian, except for the 0 f of x is going to go to the second column. The first column stays the way it is, y1, y1 prime. But the second column is going to be replaced with 0 f of x. So that's going to be 1 over negative 5 x cubed 3x squared 0 2x squared. And that's going to be negative 1 over 5 times x cubed 2x squared minus 0. That's going to be negative 2 over 5x to the fifth. Integrate that, we got u2 equals integral negative 2 over 5x to the fifth dx. I believe it's negative 1 over 15 x to the sixth. And now we can take u1, u2, y1, y2, put it together to write down the y particular. So y particular equals u1, y1 plus u2, y2. So that's going to be u1 is going to be 2 over 5x. y1 is going to be x cubed plus u2 negative 1 over 15 x to the sixth. y2 is going to be x to the negative 2. And it's all together end up to be 1 over 3 x to the fourth power. And then we can write down the general solution, c1 x cubed plus c2 x to the negative 2 plus 1 over 3 x to the fourth. Any questions? And at the very last step is write down the solution interval for this general solution. Really just let's look at the terms with x. We have a cubic, we have a quadratic, quadratic. X could be anything, but then we have a negative 2 exponent, which means that's going to be in the denominator if we rewrite it with a positive exponent, so x cannot be 0. In fact, that was given in the beginning, right? So you can write as negative infinity to 0 or 0 to infinity. Questions? Does that kind of make sense? It's the process is the same. I understand completely that if you use the exponential e to the from x, then it's probably not easy to integrate at some point. But I would say that as long as you feel comfortable with the process, the formulas are correct, that means you understand it well. Okay. Any other questions about the exam? I think this is just Professor Gibson question.
like, I didn't write it on mine, but I looked everywhere to see if we did it before the exam, but I don't know if it's just like general knowledge, but I didn't write it in some interval question mark on those ones, so.
That's
it's gonna be instructive for both problems.
yeah.
Oh,
It's okay. I would say that I never, when I solve a problem like this, oh, thank you. I never really like find solution intervals, but I think Professor Gibson somehow feel that's very important.
I was thinking about just stressing out doing that actual problem.
Right, yes. Well, if you want, you can just write an email, say like, oh, I forget to find both for both problems, can I get at least 5 points back?
Yeah.
Yeah, okay. Yeah. Yeah, that's just something he put in almost every question.
This morning I did the integration by parts for both twice for U1 and U2.
Oh yeah, I know it's a lot of integration.
There's a lot of
Yeah, definitely. I would say, like always, right? If you feel like you can demonstrate like how to solve it, how to use the required technique to solve the problem, I would say it's definitely worth to fight for a little bit more points if you want. Yeah. Unfortunately, I cannot change anything there. Yeah. But also keep in mind that you don't have to do the final project, so you just get 10 points anyway, so that's what's kind of like, I would say kind of treat that as a little bit curve for the overall grade. Any other questions? No. All right, the next thing I wanted to talk about is just kind of follow what Professor Gibson did in lecture last time, talk about Laplace transforms. So the way I kind of think about Laplace transforms is that, so obviously, we have problems, we have functions f of t, and then we have differential equation with y prime, y double prime, and f of t, all those, right? So Laplace transform is that it takes a function of t, convert it into a function of s that might be easier to integrate or to find the solution to differential equation. So there are two things I think it's important is that if we have some function f of t or f of x, when we apply this Laplace transform, this curly L, cursive letter L, and then we can end up with a new function, but with s as the independent variable instead of t. And it might be easier to work with this function instead of this one. So that's what the transform we need to do. Sometimes you might have a differential equation, for example, like a y double prime of t plus by prime of t plus cy of t equals, I don't know, just say g of t, for example. You look at it, it may not be easy to find a solution. But with the Laplace transform and with the initial value conditions, we might be able to convert it so that instead of finding a solution directly from the differential equation, when we apply Laplace transform, we end up with a different equation, capital Y of s is equal to some terms. This is not a differential equation, this is actually an algebraic equation. It means that we kind of completely bypass the whole trouble with solving differential equations. We just somehow get some algebraic equation easy to solve. And then we can apply the inverse Laplace transform to get the y of t back, which is the solution to this differential equation. But it might be very difficult to go from here to there directly. That's why we kind of go around. Do the transform it back to get this solution. So that's kind of the benefit, in my opinion, for now. So that's the Laplace transform. Let's look at some examples. So the first example is we're going to find Laplace transform of a function f of t. Let's just say the function is e to the negative 4t, for example. Let's just say we don't know any shortcuts. All we have is the definition. Can we translate this using Laplace transform to get a different function in terms of s, not t? So to work with the definition, so the definition is when we take the Laplace transform of f of t, what we do is we're going to apply this definition, which is the indefinite improper integral, from 0 to infinity, e to the negative st, f of t dt. So this definition is well defined. You can't change anything. When you use it, you have to make sure it's in this form. S here is obviously the variable, but when we look at the integration, we integrate with respect to t. So here we treat this s as a constant, but keep in mind that at n, s is not a constant, it's a variable. And sometimes there's a notation we can denote it as capital F of s. You can think about this as we're converting f of t into the function of s, a new function. So let's apply this definition to the example. So f of s is equal to Laplace transform of e to the negative 4t. I'm just going to take e to the negative 4t as f of t and solve it into this part and keep everything the same. So that's going to be from 0 to infinity e to the negative st times e to the negative 4t dt. And we just have to integrate, really. Before we integrate, maybe we can simplify those two terms by combining exponents. So that's going to be integral 0 to infinity e to the negative st minus 4t, so that's going to be e to the negative s plus 4t dt. Questions? I don't know if you remember, for improper integrals, when you linear calculus 2, when you try to integrate this, you have to using a limit definition because we can't plug in infinity directly, right? So we're going to have to rewrite this using a limit definition. So that's a limit. Introduce a dummy variable capital T goes to infinity from 0 to capital T e to the negative 4 plus, s plus 4 lowercase t dt. With this t here, assuming that some value approaching infinity is not infinity, right? So we can actually find the antiderivative, plug in 0, plug in t, then we take the limit. So that's going to be limit t goes to infinity. If we find the antiderivative here, it's exponential, that's going to be e to the negative s plus 4t. But when we take the derivative, we want to end up with this. So we have to kind of cancel this extra part when we take the derivative. So we need a coefficient 1 over negative s plus 4 in front. That means when we take the derivative to get here, we get an extra negative s plus 4 will give us a 1 more positive coefficient. Evaluate it from 0 to capital T. Plug in 0, plug in capital T. Limit T goes to infinity. what do we have? We have 1 over negative s plus 4. Again, s here, don't worry about what it is. It's just treat it as a constant when we work with t or whatever, lowercase t or capital T. So that's going to be e to the negative s plus 4 capital T minus e to the negative s plus 4 times the 0, which is good. When we have a 0 in the exponent, whatever the rest is, this part becomes 1. When we have t here, it's not bad. When we take the limit of t goes to infinity, if that part goes to infinity with a negative in front of that, the negative infinity, which end up goes to 0, right? Obviously, s is some kind of constant. So this part is going to approach 0. This part is going to go to 1. Which actually equals 1. With a negative between. So we just end up with 1 over negative s plus 4 times negative 1. We get 1 over s plus 4. So this function at the end with s is what we call the Laplace transform of e to the negative 4t. So we go from a function, exponential function e to the 4t, end up with a function with a fraction, 1 over s plus 4. So we did this Laplace transform. Questions? Obviously, you don't have to do this every time, because there's actually a table of common functions that you can memorize and use it in the future. So if f of t is 1, just a number 1, then the Laplace transform of that so the left side is the function of t, the right hand side is the Laplace transform. It's just going to be a 1 over s. It's just that's something that good to memorize in the future when you see that, oh, 1 over s or 1, they're kind of like the Laplace transform of each other. So, one of each other. 1 over s is the Laplace transform of 1. And then if you have f of t being t, then that's going to be 1 over s squared. If you have t to the power of n, that's going to be n factorial over s to the n plus 1 in the exponent. By the way, I just want to say that, everywhere you look on the internet, you're going to find a table. So even if you don't write it down now, let's just say you need it in the future when you do your homework, you can always look it up. It's also in the lecture notes. Okay, make sure I didn't write anything wrong there. And then if we have e to the at, the Laplace transform is going to be 1 over s minus a. And look at our example. We have e to the negative 4t, right? So note, in our example, we have e to the negative 4t. So you can kind of think about the a here corresponding to negative 4, so the Laplace transform is 1 over s minus negative 4 becomes s plus 1.
On the exams, exams, would a table be provided, or you just need to know it?
I think you have to know it. Okay. I don't think it will be provided. But I could be wrong. Assuming it's not provided for now. Another one you can memorize that e to the negative at, which is just 1 over s plus a. If you have a negative exponent, it's come up addition. And then there's like a sine and a cosine. Don't worry, we're going to write down those next time. But I want to point out that if f of t is just y, like a y of t, for example, then the Laplace transform, we just use capital Y of s instead of capital F of S. And the next two are more important because you're going to have to use it a lot when you solve differential equations. The first one is the derivative of y, which easier if you remember that it's just going to be S times capital Y of S minus lowercase y of 0. Now I want to kind of explain the terms here. So if you have y, the Laplace transform we just use a capital Y, right? Depending on some S there. If you have the derivative of y of t, then the Laplace transform is going to be S times the Laplace transform of y, so the capital Y of S. This S just means the input is S. This S is a variable S. Minus y of 0 means in the original y of t function, we're going to plug in 0 there to figure out what that value is. So this y of 0 usually is the initial value that you should be given. So this is the initial value usually given. So you don't have to worry about how to find it. Usually you can just, actually you can't find it because we don't know what y of t is. But that will be given, so you can just take the value for it. And then the next one is for the second derivative, which is going to be s squared y, capital Y of S minus S times lowercase y of 0 minus y prime of 0. Again, the y prime of 0 is just the initial value will be given, just like the y of 0. Because we don't know what y of t is, right? So there's no way we can actually find them by plugging 0. So I would say that if you feel good, maybe you should memorize it. It will be handy a lot of times. Save a lot of time. Especially the last two, I would say very important. Because you have to, well, you should know them if you want to use Laplace transform to solve differential equations. Any questions before we talk about example? All right, here's the example. So we're going to solve this initial value problem, 3y prime equals 1 with initial condition y of 0 equals negative 1. And obviously, if I just ask you to solve this, I'm pretty sure you can solve it correctly without, too much time or too much trouble. Because all you have to do is find, dividing by 3, finding the antiderivative, follow the initial condition to find the c, and plug back in, that's all. Fairly straightforward, right, first order equation. But we're going to use this example to practice Laplace transform. So what we're going to do, the first step, using Laplace transform is that we're just going to take that equation, we're going to take the Laplace transform of the entire equation. It means take the Laplace transform of every term there. So Laplace transform of the equation 3y prime equals 1, and which is equivalent to taking the Laplace of each term there, 3y prime, Laplace of 1 on the right hand side. This constant 3, we can put it outside of the Laplace there. So the 3 becomes Laplace, so just 3 is outside, so 3 times Laplace transform of y prime equals Laplace transform of 1. So that's the first step. And obviously we have to know what each of the Laplace transform is, right? So how do we find that? So the shortcut is that you go to the table, and find the corresponding one. So for example, if we want to know what the Laplace transform of the y prime is, it's right there, the second to the last line in the table. So that's just going to be s y of s minus y of 0. So that's what this first Laplace transform will give us. We're going to use it. Multiply by 3, obviously. And then what about Laplace transform of 1? Well, we had that earlier, right? The first row of the table is give us 1 over s. So that's going to be 1 over s. As you can see, by doing this, we basically take a differential equation. We didn't really integrate or anything. What we do is we do the transform, we end up with some algebraic equation with s, with y of s. So this is some number we can plug in. This is s. So now we're going to plug in the y of 0. So we get 3s times the y of s minus the negative 1 equals 1 over s. So this is a algebraic equation. We avoided the whole thing about solving differential equation. So that's the first step. Step 2. Well, any questions about the first step? Again, the table probably is your favorite friend at this point. And then we're just going to solve for the capital Y of s, because that's something we need at the end. So solve for capital Y of s. So I'm going to divide by 3 and then manipulate all the terms. So I get s times y of s plus 1 equals 1 over 3, 1 over s, minus 1, 1 over 3, 1 over s, minus 1, divide by s, y of s equals 1 over 3, 1 over s, minus 1, divide by s, and then split the fraction into 2. So I get 1 over 3, 1 over s squared, minus 1 over s. Any questions about what I did? So this is what y of s is. Remember that y of s, note, y of s is equal to Laplace transform of y of t by definition. But we found the Laplace transform. We have to solve for y of t at the end. So the last step, step 3 is to find y of t, the solution to the differential equation, using inverse Laplace transform. So if you go back here, so y of s is Laplace transform of y of t. So if I add an inverse Laplace to both sides, I should have the inverse Laplace of y of s equals inverse Laplace of Laplace of y of t. The inverse and the Laplace transform, they should cancel, just give me y of t left. Therefore, y of t is just equal to inverse Laplace of y of s. So at the end, if I want to find y of t, we're going to take whatever the y of s is and then apply the inverse Laplace transform. So in the end, I want to find y of t. That just equal to inverse Laplace of y of s. I know I'm like repeating a lot. So that's going to be inverse Laplace of 1 over 3, 1 over s squared minus 1 over s. And we're going to apply the inverse Laplace to every term, each term there. So that's going to be inverse Laplace of 1 over 3, 1 over s squared minus inverse Laplace of 1 over s. Bring the 1/3 outside. So you got 1 over 3 inverse Laplace of 1 over s squared minus inverse Laplace of 1 over s. I'm almost done here. I know you probably want to go home too. Any questions? This is just a notation. In the future, you can probably skip quite a few steps. But for now, I just want to show you every single step. Okay, so how do we see we have 1 over s squared? How do we find the inverse Laplace of that expression? The table again. So now we're going to go to the table. So the table earlier tells us that if we have a function of t, we can get function of s by taking the Laplace transform going from here to there, right? But now we have something on the right hand side, we want to apply the inverse Laplace. That should take us back to the f of t. So we're just going to look for 1 over s squared here and then figure out the corresponding t function, which is this part. So if we have 1 over s squared, we take the inverse Laplace, we should get a t out of it. So that's what the first inverse is. That part becomes t. So we get 1 over 3 times t. And what about the 1 over s, Laplace, inverse Laplace of 1 over s? Again, if we go back to the table, 1 over s, 1 over s is here. If we apply the inverse Laplace transform, we should get f of t, which is 1. So this part becomes 1. That's it. So that's a lot of translating, going from a function of t to a function of s, and then from function of s to function of t at the end. And this is solution to given differential equation. 3y prime equals 1 with the initial condition. So we don't have to plug in the initial condition because we already done that when we did the Laplace transform. Questions? Does that kind of make sense? Obviously, that's like a more complicated example, right? It's not going to be this straightforward when we go from that part to here. You might have to do a little bit more work. Usually, partial fractions. It's required in that process. That's actually the next thing I'm going to ask you to do, to review on your own. So review partial fractions. So partial fractions is that you take one fraction, you decompose it into a series of simpler fractions. A couple examples for you to kind of try on your own, in case you forget, is the first one is 5x minus 4 over x squared minus x minus 2. And this one you can decompose it into two fractions. I don't know what the denominators are, but you can find them. But numerators are a and b, I believe. The second example I have is 1 over x minus 2 cubed. This is a linear factor in the denominator, but it has a power 3. So we should be able to decompose this into 3 partial fractions. And I actually should have done this, but You can try see what you find out. So that we can decompose this into A over x minus 2 plus b over x minus 2 squared plus c over x minus 2 cubed. I probably should work out the steps, figure out what ABC over there. But that's something for you to think about. And then the next one is x squared plus 15 over x plus 3 squared times x squared plus 3. So this one, when we decompose it, to find the partial fraction, the first denominator, x plus 3 squared, will give us two fractions that looks like those two, with the power increased by 1 each time. But those linear factors, right? So that will give us some constant a over x plus 3 plus another constant b over x plus 3 squared, I think. And then this x squared plus 3 term in the denominator is a quadratic factor because we cannot simplify further. We cannot factor that. So that's going to give us a new term, x squared plus 3. Does anyone remember what the numerator should be? If we... Excellent. Exactly. So great. So it'll be cx plus d. It'll be a linear because this is a quadratic, so the numerator should be linear. This is a linear factor, so the numerator should be a constant. Even though this is if you just look at together, that's quadratic, but we only look at the factors. See if that's a linear or quadratic. Okay, so if it has been a while, definitely practice those problems. Maybe review your notes or look up on the internet. You need to know this maybe for the next lecture or maybe the one after. All right. Anyway, I should let you go. It's actually time.